Hi, I'm Johan Klockars from Cobham Gaisler, and I'm here to talk about NOEL-V, a new high-performance RISC-V processor family. Gaisler has been in the space processor business for over 15 years, and this is our mission statement. Our Leon-based chips and IP can be found all over the solar system. While these are not RISC-V processors, we have always used an open architecture. So why are we adding RISC-V to our processor core portfolio? Well, we've had requests for a 64-bit architecture from customers, and RISC-V fits that well, and it's open and has momentum. The RISC-V software ecosystem is lively, and the European Space Agency is positive to using RISC-V in space. On the implementation side, RISC-V is also not overly complicated. Why then not license the core from someone else? Well, we have an experienced processor team in-house, and if we do it ourselves, we'll have full knowledge and control over the design, making it easier to add the fault tolerance features we are known for and other custom modifications. Of course, we also want to take advantage of our existing IP infrastructure, GRLIB. Finally, this allows us to have flexible licensing. We have for many years made our cores available under the GNU General Public License and want to continue doing so. This allows anyone to use and modify the code at will for research, evaluation, or whatever, but it can't really be used in circumstances when you can't release your own source code as well. So for this, we have a possibility to add a commercial licensing. Here is a somewhat random collection of IP cores from GRLIB. The important thing to note is that some basic features, including the processor cores themselves, are available under the GPL. A commercial license adds extra IP, and there's also a fault-tolerant license. Now that the NOEL-V is in GRLIB, it's simple to use the rest of these IP cores with a RISC-V CPU. We are currently in the process of making sure that all the IPs work with the little endian buses. While GRLIB contains processors, peripherals, and memory controllers, it's not simply an IP core library, but rather a complete design environment. There are GUI tools for configuring IPs, and also a script environment that can generate project files for various EDA tools and launch them. All our code is written in VHDL, but at the lowest level, we instantiate abstractions of major components, which then map to various FPGA and ASIC technologies. So, what did we end up doing? The NOEL-V is the RISC-V RV64GC, that is Linux compatible. We have Linux up and running on it, and you can try it yourself by downloading bitstreams for various FPGA boards. To significantly improve performance over previous generation cores, we went with a dual-issue pipeline, and the initial Christmas 2019 release of the NOEL-V has been clocked at 4.7 Coremark per megahertz on hardware. This was using quite a few GCC flags, but we haven't gotten around to making GCC optimized for the NOEL-V yet. Development is still ongoing, and currently we are targeting more than 100 MHz on the Xilinx UltraScale FPGA. In a bit more detail, we have the 64-bit integer instruction set with hardware multiply and divide, as well as atomics, floating point, and compressed instruction support. The FPU we are releasing under the GNU General Public License is designed to be small rather than fast, and even for simple operations it uses half a dozen cycles or so per operation. But it will run in parallel with the integer pipeline when possible. For commercial licensing, we will be adding a modified version of our GR-FPU, which is fully pipelined and currently does most operations with a throughput of 1 per cycle and a 4-cycle latency. It does divide in 16 cycles and square root in 24. Compressed instructions are unfortunately not enabled by default in the current release. We support all normal CPU modes, of course, and there is a standard RISC-V virtual memory as well as physical memory protection. Upcoming extensions include hypervisor, user-level interrupts, bit manipulation, and RV32, where all the 32 builds are actually working in simple tests right now, but we haven't gotten to actual verification. The current implementation uses a 7-stage dual-issue in-order integer pipeline, where the 2 lanes have some differences, but they both contain full ALUs. To help with performance in the presence of dependencies, there is actually a complete extra set of ALUs and branch unit late in the pipeline. We have branch prediction as well as a return address stack to avoid unnecessarily flushing the pipeline. The level 1 instruction and data caches can be up to 16 KB each. I'll just mention a few more details on the into the pipeline here. Please note that optimization work is ongoing for both FPGA and ASIC targets, so it's possible that details may change. In the fetch stage, we're using both the branch predictor and the branch target buffer in an effort to make sure that we don't stall the pipeline on branches when it's not needed. We continue the branch handling in the decode stage, where a return address stack is used, and we also deal with non-conditional branches here. The decode stage is also responsible for figuring out if the next two incoming instructions can run together through a pipeline or not. Due to the late ALUs and branch unit, that may be possible even if one depends on the other. But there are other cases where they may have to execute alone. For example, when there are limited resources in the pipeline, such as there only being a single multiplier or conditional branches only being handled in one of the lanes. Since there are some differences between the two lanes, the decode stage may let two instructions swap places if that helps. Then in the register access stage, we check whether the instructions can execute early or must be delayed to later in the pipeline. Or if perhaps there are dependencies we can't meet at all, the pipeline will insert bubbles here as needed. The memory stage will stall the pipeline completely if it can't provide data immediately from cache on reads or push data to the store buffer in time. Some further details on the MMU and caches. While the code was written to support all currently defined RISC-V page table configurations, we have only really tested 39-bit virtual addresses so far. Actual physical addressing can be configured. There are separate fully associative translation look-aside buffers for instruction and data, and we are currently building with 8+8 entries. Physical memory protection can be used even with the MMU active. All page tables activities are handled in hardware. While RISC-V does not actually define a cache and thus the concept of uncacheable areas, we are experimenting with support for it in the page tables, but we can also hard code it. Our level 1 caches are single cycle access and can use up to 128-bit wide AHB buses towards L2 cache memory for quick cache line fills. They are virtually indexed but physically tagged, and we also support address space identifiers, although we haven't really had an operating system to test that with. A replacement policy is least recently used, and we support up to 4-way set associativity and 16 KB per cache. To ensure that we can sustain 2 instructions per cycle, the instruction cache delivers 64-bit per cycle. The data cache is write through, and we use snooping for coherence between multiple cores, and there is a store buffer to improve write performance. We have a level 2 cache available, although not under the GPL license. It has both AHB and AXI4 backends up to 128-bit wide. Address ranges can be configured as either write through, write back, or uncached. Associativity is also 4-way here, and it can be split between cores, and the size goes up to 2 MB. When available, we strive to follow the RISC-V standards, and that includes supporting the standard debug module. And there is direct access to both general purpose and the control and status in the CSR registers, and there is a program buffer that can be used to implement other debug functionality. Regarding triggers, we currently support matching and instruction count. Our own debugger, grmon, of course, supports the NOEL-V as well. And we also have a standard RISC-V platform level interrupt controller. Finally, a little bit about configurations and SOCs. NOEL-V is a family of cores based on the same actual code base. It will go all the way from tiny 32-bit single-issue microcontrollers without either cache, memory protection, or FPU, all the way up to the high-performance variant I've been talking about here. In the middle, there are things like a low-performance 32-bit core, which could still be fully Linux capable. We will provide these as subsystem configurations, including some basic peripherals, and they will be fully verified by us. Of course, it will still be possible for users to create something different by playing around with the configurations themselves. As I mentioned, we do our own chips, and will of course use the NOEL-V for some as well in the future. Even I don't know what they will look like or when they might show up, but since we've done quad cores in the past, it seems likely that we will eventually go further. If you want to know more about the NOEL-V or its sister architecture, the Leon-V, please follow links from this presentation or get in touch with us. Thank you for watching.